Let's talk about questions as well as answers based on structure equation modeling. Number one question, that is, what is the difference between a latent construct and measured variable? Let's first talk about the latent construct. And the latent, we call it latent variable, is like a true score that is not directly observed. The observed variable is the measurement that is directly observed, and some degree of random measurement error may exist, such as the observed score does not perfectly match the true score. For example, height, weight, and age all are observable variables because they can be directly measured. A latent variable, one on the other hand, it is variable that cannot be directly measured or observed, but it is preferred from observed variable. Latent variable. Latent variable and observable variable are concepts in a statistical modeling and data analysis. Let's talk about an observable variable. It is a variable that can be directly measured or observed in a study. For example, height, weight, and age are all observable variable because they can be directly measured. If we talk about a latent variable, on the other hand, is a variable that cannot be directly measured or observed but is its interface from observable variable. For example, intelligence is a latent variable because it cannot be directly measured, but it can be inferred from observable variables such as test score and academic achievements. Latent variables are often used in statistical structure equation modeling, which is a statistical technique used to analyze two relationships between multiple variables. In this approach, the relationship between variables are represented by a model that includes both observable variables and latent variables. The model specifies the relationship between the variables, and the value of the latent variables are estimated based on the observable variable. In summary, observable variables are variables that can be directly measured or observed, while latent variables are variables that cannot be directly observed but are interfaced from observable variables. Latent variables are often used in statistical modeling to represent underlying construct or concept and cannot be directly measured. Let's talk about some examples. Suppose you are conducting a study on a relationship between exercise and heart health in a group of adults. Here are some variables that could be involved: observable, independent variable. Exercise level, we call it measured in hour per week. Observable variable outcomes, heart health measured as a score and a cardiac health index. Confounding variables, these are the different type of the variables. The first is observable variable, which we can observe. Suppose they gave the example of exercise, so exercise we can observe based on hours. Observable outcome variable, that is heart health, that is measured score is a cardiac health index. Confounding variable, age measured in years. So the variable which we can measure in a year, a direct factor that may affect both independent variable and outcome, and it's measured in our study. If we talk about the latent variable, that is fitness level, cannot be directly measured but it interfaced from observable variables such as exercise level and heart health. Lucrating variable, dangerous factor for our study. Diet is not directly measured in the study, but it could potentially affect both exercise level and heart health. For example, individuals who eat a healthy diet may also be more likely to exercise regularly and have better heart health, while individuals who eat a poor diet may be less likely to exercise and have worse heart health. In this example, exercise level is the observable independent variable, heart health is the observable dependent variable, age is a potential confounding variable, and fitness level is a latent variable. Age could be a confounding variable because it is related to both exercise level and heart health, and could distort the relationship between these variables if it is not controlled for in the analysis. Fitness level is a latent variable because it cannot be directly measured but is interface from the relationship between exercise level and heart health. If that is not taken into account in this study, it could potentially confound the relationship between exercise level and heart health, leading to incorrect conclusions. Therefore, diet could be a lucrative variable in a study on the relationship between exercise and heart health. Overall, this example illustrates how these different type of variables can be involved in the study and how they can be used to help researcher understanding the relationship between the variable of interest. A latent construct and a measured variable are both fundamental concepts in a statistical research, particularly in a field of psychology and science, social science. Here, the difference between both of them. Latent construct, we call it the latent variable, and measurable variable, we call it manifest variable. A latent construct is a variable that is not directly observable or measurable, but it is interfered from other variables that are observable. If we talk about the measure variable, let as it is clear by their name, a measure variable is also known as the manifest variable, is a variable that directly observable and the measure or a qualified. If we talk about again latent construct, that is it represent an underlying unobservable attitude on concept that the hypothesize to the exist or the influence observed variable. But the manifest variable, that is the measured variable, are concrete and observable phenomena such as responses to survey questions, score and test, or physical characteristic like height or weight. Latent constructs are often theoretical concepts such as intelligent attitude, personality traits, and social economic status. If we talk about measure variable, that is unlike the construct, measure variable do not present underlying concept of construct. Instead, they provide direct observation or measurement. Latent constructs are often theoretical concepts such as intelligence, attitude, personality, and the social economic status. They are typically measured indirectly through the observable indicators or manifest variable using the statistical techniques such as the factor analysis or structure equation modeling. Measure variable, they provide direct observation or measurement. Measure variable are often used to assess the operationalized latent construct in research studies by capturing aspect and dimension of the construct through the observable means. In summary, while latent construct represent observable theoretical concept, measure variable are directly observable and quantifiable. Latent construct are interfaced from the measured variable, which serve as indicator or proxies for the underlying construct. Let's talk about the second question, that is the what are the distinguishing characteristics of structure equation modeling. If we talk about the its characteristic is structure equation modeling is a powerful statistical technique used to test and estimate complex relationship among the variables. Is distinguished characteristic including first, integration of measurement and structure model. Structure equation modeling allow for the simultaneously examining or measurement model the relationship between latent construct and their observed indicators, and structure models the relationship between the latent construct themselves. This integration enables researchers to assess the validity of measurement instrumental, for example, the questionnaire, and examine how latent constructs are related to each other. Second is modeling of the latent construct. These are the characteristics of structure equation modeling. If we talk about the modeling of latent construct, that is structure equation modeling is a particularly variable for modeling latent construct are Variables that are not directly observable but are inferred from observed variable. It allowed researchers to account for measurement error in the observed indications and estimation the relationship between latent construct accurately. Number 3, specification of complex relationship. Structure equation modeling can handle complex relationship among the variables, including direct and indirect effects. Mediation, moderation, and latent variable interactions. Research can be specified both hypothesized and exploratory relationship with a single model provide a comprehensive understanding of the underlying mechanism. Assessment of model fit. Structure equation modeling provide various fit indices and statistical tests to evaluate how well the proposed model fit to observed data. Common fit indices to include chi-square test, comparatively fit test, Tucker like index, and root say mean square error of approximation, and standardized root mean square residual. Handling a multivariate data. Structure equation modeling can analyze multivariate data set with multiple dependent and independent variables simultaneously. It accommodates both continuous and categorical variable, allowing for the analysis for diverse type of data. Model modification and comparison. Structure equation modeling allow researcher to identify model by adding or removing path, testing alternative hypotheses, and comparing competing models using fit index and statistical test. This iterative process enables the researcher to refer their theoretical model based on empirical data. In instance, structure equation modeling offer a comprehensive framework for testing complex theoretical model, integration, measurement and structure components, and assessing model fit and validity. It's widely used across various disciplines including psychology, sociology, economics, and epidemiology to examine relationship among the variable and test theoretically hypotheses. Number 3, the question number 3, that is describe the conceptually how the estimated covariance matrix in a structure equation modeling analysis. And fourth question can be computed. Why do we compare it? So first we talk about the conceptual how the estimate covariance matrix in structure equation modeling. In structure equation modeling, the estimation covariance matrix play a crucial role in a model estimation, assessment and comparison. Here's a conceptual description of how it is compute and why it's compared to sample covariance matrix. Number 1, computation or estimated covariance matrix. In structure equation modeling, the estimated covariance matrix represents the covariance structure implied by the specified model. It compares two components, the covariance among observed variable, manifest variable, and the covariance among the latent variable if present in the model. The covariance among observed variable is determined by the partner estimated path coefficient in a structured model. The covariance among latent variable is determined by the factor loading in the measurement model and the variance of the latent variable. Comparison to sample covariance matrix. The sample covariance matrix is computed from the observed data and represent the empirical covariance structure in the sample. It provides information about the pairwise relationship among the observed variable. Comparing the estimation covariance matrix, that is sigma, to the sample covariance matrix allow researcher to assess how well the specified model fit the observed data. This discrepancies between sigma and S index between the model implied covariance structure and the actual covariance structure in data. Goodness of fit index in a chi-square test. Comparatively fit index. Tucker-Lewis index. TLI root mean square error or approximations. We call it RMSEA, and the standardized root mean square residual SRMR are used to be evaluate the fit of the model by assessing how well sigma match S. A good fit is indicated by small discrepancies between sigma and the reflected in low values of fit index and statistical test. In summary, the estimated covariance matrix, that is sigma, in structure equation modeling represent the covariance structure implied by the specified model, while the same covariance matrix S represent the empirical covariance structure in the data. Comparing sigma to S allow researcher to evaluate the fit of the model to the observed data and assess how well the model represent the underlying relationship among variables. Next question we will discuss, that is how is the structure equation modeling similar to other multivariate techniques. In structure equation modeling, the estimated covariance matrix play a crucial role in a model estimation, assessment and comparison. Here conceptual description of how it's computed and why it's compared to the same covariance matrix. Let's talk about the first computation and estimation covariance matrix, that is sigma. In structure equation modeling, the estimation covariance matrix, that is sigma, represent the covariance structure implied by the specified model. It compares two components, the covariance among observed variable, manifest variable, and the covariance among latent variable if present in the model. The covariance among the observed variable is determined by the parameter estimate path coefficient in a structure model. The covariance among the latent variable is determined by the factor loading is the measurement model and the variance of the latent variable. Let's talk about the comparison to sample covariance matrix. Sample covariance matrix is computed from the observed data and represent the empirical covariance structure in a sample. It provides information about the pairwise relationship among the observed variable. Comparing the estimated covariance matrix, that is sigma, to the sample covariance matrix as allow researcher to assess how well the specified model fit the observed data. Discrepancies between sigma and S indicate difference between the model implies covariance structure and the structure covariance structure in the data. Goodness of fit index such as chi-square test, comparatively fit index, Tucker-Lewis index, and mean square and approximate RMSEA of standardized root mean square residual are used to evaluate the fit of model by assessing how well the matches. A good fit is indicated by small discrepancies between the sigma and the S reflected in low value of fit index and statistical test. In summary, the estimated covariance matrix, that is sigma, in structure equation modeling represent the covariance structure implied by the specified model, while the sample covariance matrix, that is S, represent the empirical covariance structure in the data. Comparing sigma to S allow researcher to evaluate the fit of the model to the observed data and assess how well the model represents the underlying relationship among the variables. How is structure equation modeling similar to other multivariate technique? If we talk about this, so this article I have taken from online. Structure equation modeling shares similarities with other multivariate technique, particularly in the approaches to analyze relationship among the multiple variable. Here there are some way in which is similar to the multivariate technique. This is the question: how the structure equation modeling similar to other multivariate technique? Answer is that structure equation modeling share similarities with other multivariate technique, particularly in approach of analyzing the relationship among the multiple variables. Here are some ways in structure equation modeling. Let's we talk about the regression analysis. Like regression analysis, structure equation modeling, relationship between variable, both technique estimating coefficient to quantify the strength and direction of these relationships. Structure equation modeling extend regression by allowing for the modeling of complex relationship including mediation, moderation, and latent variable beyond the simple linear relationship. Factor analysis, structure equation modeling and the factor analysis both are relationship among the observed variable and latent construct. Factor analysis can be seen as a special cases of structure equation modeling where only the measurement model relationship between the observed variable and the latent construct is specified without the inclusion of structure model relationship between the latent construct. Structure equation modeling extend factor analysis by incorporating both measurement and structure model, allowing for a more comprehensive understanding of the relationship among the variable. Path analysis. Let's talk about the path analysis. Path analysis is a precursor to structure equation modeling and share many similarities with the structure equation modeling component of structure equation modeling. Both techniques involve specify a set of hypothesized relationship among the variable in a direct acyclic graph DAG format. Structure equation modeling expand upon path analysis by allowing the simultaneously estimation of measurement and structure model, accommodating latent variable and providing a more robust framework for model evaluating and comparison. Covariance structure analysis. Structure equation modeling, the covariance structure analysis are closely related as a both technique involve the estimation and evaluation of covariance matrix. Covariance structure analysis focus of primarily on estimating covariance structure based on observed data, whereas structure equation modeling integrates measurement and structure models to estimate covariance metrics that reflect both observed and latent variables. Structure equation modeling extended covariance structure analysis by allowing for the test of complex theoretical model and the assessing of the model fit in using various fit indices. Multivariate, multivariate analysis of variance MANOVA. Like MANOVA SAN can handle multivariate data with multiple dependence variable. SEM goes beyond MANOVAs by allowing the examination of relationship among the both independent and dependent variable, as well as the inclusion of the latent variable and complex model structure. In summary, while each multivariate technique has its unique feature and application, structure equation modeling shares similarities with that technique is focus on modeling relationship among the multiple variable and its ability to handle the complex data structure. However, structure equation modeling distinguished itself by integrating measurement and structure model, accommodating latent variable and providing comparative framework for the hypothesis testing and model evaluation. Let's talk about question 5, that is a what is the superior correlation, how might be relatively using structure equation modeling. Theory is a systematic and coherent set of the principal concept or the positioning explain, and theory it is the systematic and coherent such as the principal concept or the proposition that explain and predicted phenomena within a particular domain of the study. It provides a framework for understanding relationship among the variable and going empirical research. In the context of structure equation modeling, theory plays a crucial role in a model specification, interpretation, and hypothesis testing. In structure equation theory is represented through the formulation of structure model which consists two main components, that is the measurement model and structure model. First we'll talk about the measurement model and then we will talk about the structure model. The measurement model represents the relationship between latent construct, theoretically concept, and their observed indicators, measured variable. They specify how observed variables are related to the underlying latent construct they are i- intended to measure. The measurement model is typically represented by factor loading, which indicate the strength and directions of the relationship between each observed variable and its corresponding latent construct. These factor loading reflect the theoretical construct proposed by the underlying theory, providing a quantitative representation of how the observed variable captures the underlying latent construct. Let's talk about the structural model. The structural model represents the relationship among latent constructs themselves. It specifies the hypothesized causal pathway for association between the latent construct and based on theoretical expectation. The structural model is represented by path or arrows connecting latent construct and indicating the direction and strength of the relationship between them. These paths are informed by theoretical construct and hypothesis driven from the underlying theory, reflecting the proposed causal mechanism or dependencies among the latent construct. By incorporating both the measurement and structure equation model provide a formal framework for testing theoretical hypotheses and evaluating the adequacy of the theoretical model. Researcher can specify their theoretical expectation regarding the relationship among variable, estimate model parameters based on empirical data, and assess how well the proposed model fit the observed data. Theory guided the formulation of the structure equation model, that interpretation of results, and the refinement of theoretical understanding based on empirical evidence. Let's will discuss about question 6, that is what is fit in the context of statistical modeling. Fit is referred to how well a proposed model represents the observed data. It assesses the degree of agreement between the model prediction and important relationship of actual pattern observed in the data. Evaluating model fit is essential for determining the adequacy of statistical model and assessing its validity for making the interface or predictions. For different type of statistical models such as regression model, factor model, or structure equation model, the concept of fit may be evaluated differently. However, in general model fit assessment involve comparing the model implied relationship or predicted values to the observed data and evaluating the context of agreement using the various fit indices or statistical tests. Common measurement of fit includes chi-square test. This test compares the discrepancy between the observed and expected covariance matrix. A non-significant chi-square value indicates good fit, suggestion that the model adequately represents the observed data. Comparative fit index and Tucker-Lewis index. These indices assess the relative improvement in a fit of the specified model compared to a baseline model value close to 1 indicate good fit. Root mean square error of approximately, we call it RMSEA, that is measure the discrepancy between the complexity smaller values of RMSEA, typically below 0.05, indicate better fit. Fourth is standardized. Standardized root mean square residual. We call it SRMR. It is the average discrepancy between the observed and the predicted covariance. Lower value and SRMR indice better fit. Acquire information of criteria AIC and Bayesian information. These indices balance model fit and company exist complexity with the lower values and indicating better fit. In summary, fit the statistical modeling refer to the degree of agreement between the model predict, predictions and the observed data. Eventually, fit is essential for determining the validity of model and estimating that its accuracy represents the underlying relationship among the variable. What is the difference between the absolute and relative fit index? Absolute and relative fit indices and two types of measurement used to assess the goodness of fit and statistical model, including structure equation model. Here the difference between them. Let's will talk about the absolute fit index and relative fit index. First we will discuss the absolute fit index and then we will discuss relative fit index. Absolute fit indices assess how well the specified model fit the observed data without the reference to any alternative model. These indices provide an absolute measure of fit by evaluating the context of discrepancy between the model implies and covariance matrix and the observed covariance matrix. Example of absolute fit index including the chi-square test, statistic, root mean square error of approximation, and standardized root mean square residual. Lower value of absolute fit indices better fit with non-significant chi-square value below a certain threshold. For example, 0.05 and SRMR values close to 0. Relative fit index. Relative fit index assess a fit the specified model relative to baseline or null model. This index models typically fewer parameters of more restrictions. These indices compared to fit of the specified model to the fit of more restricted model such as a null model as a saturated model. For example, of relative fit index including the comparative fit index CFI and TLT, AIC, CFI and TLT close to 1 indice before the compared of the baseline model, while over the value of information criteria AIC and BIC indice better fit and lower model complexity. In summary, absolute fit indice provide a direct assessment of how well the specified model fit the observed data, whereas relatively fit indices compare the fit of the specified model to that of the baseline model or other competing models. Both type of fit indices are important for evaluating that adequacy of the statistical model and determining the whether it's provide a good representation of underlying relationship among the variable. Let's talk about the 9 question. What is this? This is how does the sample size affect the structure equation modeling. Let's talk about its answer. That is, sample size plays a crucial role in a structure equation modeling. It can impact the reliability, stability and generalizability of structure equation modeling result. Here are several ways in which sample size affects structure equation modeling. Let's will discuss statistical power, precision of parameter estimation. These are the way, and model stability, model complexity, model assessment. Let's we'll discuss one by one. First we'll discuss statistical power. That is, larger sample size generally result in a greater statistical power, allowing for more piece of estimation of model parameters and increase to detect significant effect. With the large sample size, structure equation model are better equipped to discuss true relationship in the data from the random reliability, leading to more reliable finding. Precision of parameter estimation. Sample size directly influence the precision of parameter and estimate in structure equation modeling with large sample size. Parameter estimation such as the factor loading, path coefficient, and latent covariance tend to be more stable and reliable as they based on the greater amount of data. Model stability. Small sample size can lead instability in a structure equation modeling estimation, particularly with complex model or models with many parameters. With insufficient sample size in structure equation modeling may be sensitive to outlier and influence cases, potentially learning to the underlying result. Larger sample size provide more robust and stable estimation, reducing the likelihood of superior finding or model misconception. Model complexity. This required sample size increase with the complexity of the structure equation modeling. More complex model, which include a large number of latent variable and observed indicators or path, typically require larger sample size to obtain reliable parameter estimate and the fit. Model fit assessment. Sample size influence the accuracy and reliability of fit indices used to evaluate the goodness of fit of structure equation modeling. Some fit indices, such as the chi-square test statistic, are sensitive to sample size with larger adjusted sample leading the smart chi-square, such as the comparative fit index CFI and the Tucker likewise index, that is TLI, are less affected by sample size and power more reliability indicators of model fit across the different sample size. In summary, sample size is a critical consideration in a statistical equation modeling, impacting statistical power, precision of parameter estimating model, stability model, and complexity. And fit assessment researchers should aim for sample size that are sufficient to obtain reliable and interpretable structure equation modeling result, particularly when analyzing complex model or conducting hypothesis testing. 10. Why are no magic values available to distinguish good fit from poor fit across all situations? There are no universally applied magic values or distinguish good fit from the poor fit across its situation and in a structure equation modeling structure equation due to several lessons. Model complexity, here we talk about, here it's a model complexity, research context and subjective judgment. Structure equation modeling allow for the specification of driven and complex models with varying number of the latent variable observed indicate and path. The appropriateness of fit index depend on the complexity of the model being tested. A fit index that indicate good fit and sample model may not necessarily indice good fit for a more complex model. In research context, the interpretation of model fit depends on the specified research context and objective. What constitute good fit may vary depend on the substantive theory being tested, the research question being expressed, and the character size of the data being analyzed. Subjective judgment. Interpreting model fit is not solely determined by statistical criteria but also involves subjective judgment. Researcher must consider the theoretical plausibility of the model, the practical significance of the relationship being examined, and the overall coherence of the significance of relationship being examined. Finding in the relationship to prior research and theoretical expectation. Relative assessment. Fit indices provide relative assessment of model fit, comparing the specified model to the baseline or alternative model. What constitutes good fit is often evaluated in comparison to fit or alternative model or theoretical expectation rather than relying on absolute cutoff values. Let's talk about the fit index limitation. What is this? This is each fit index has its own strength, weakness, and assumptions. Different fit index and lead to conflicting conclusion about model for highlighting the importance of considering multiple indices and conducting sensitivity analysis. Sample size and data character size. The appropriate of the fit index can be influenced by the sample size, data distribution, and other data characteristics. Fit indices that are less affected by the sample size, such as CFI and TLI, may provide more reliable indicator and model fit across different sample size. In summary, the observed magic values, good fit from poor fit across all situations, reflect the complexity, subjectivity, and context dependency of model evaluating in a structure equation modeling. Researchers should interpret fit indices curiosity, considering the specific characteristic of the model, the researcher context, and overall theoretical framework. Question number 11, that is draw a path diagram with two exogenous construct and endogenous construct. The exogenous constructs are each measured by 5 items and the endogenous construct each measured by 4 items. Both endogenous construct and are expected to be negatively to endogenous construct. Here is the exogenous item 1 2 3 4 5, endogenous 1 2 3 4 5, endogenous item 1 2 3 in the diagram. Exogenous and endogenous are two ex- uh, exogenous construct. Each exogenous construct is measured by 5 items, 1 through item 5. The arrow points the exogenous construct to be endogenous construct, indicating negative relationship. And endogenous, it is the endogenous construct measured by the item, that is 1 through the item. The path diagram usually represent the relationship between the construct and their respective indicators as described.